Derive the Euler-Lagrange equation for the following minimization problem. To solve this, we have to find the directional derivative. So we want our derivative to be 0 at the minimum. Therefore, we would write 0 is equal to, and let's let t be the real number, and we're going to evaluate it at 0. Evaluate what at 0? Evaluate phi of u plus t times v for any vector v. Okay? But all we have to do now is plug it in. Plug u plus tv into our equation here. Wherever our u appears, we put in u plus tv. Therefore, we'll be evaluating the directional derivative of the integral of the gradient of u plus tv squared plus u plus tv minus u naught. And of course we have dx. And first of all, we have to realize that we are deriving with respect to t. And therefore, some of these terms are not going to matter. For example, I forgot a squared here. And actually, let's work this out a little bit. Okay, so we still have our derivative, but now we're going to have, so gradient is a linear operator, right? So we can distribute it out inside the sum, and we're going to end up with the gradient of u squared plus 2 times t, gradient of u, gradient of v, plus t squared, gradient of v squared. Now, this whole part, this part that I wrote here, is the first part of the sum. Okay, and I can do the same thing for the second part of the sum. And because this is our first question, I'm just going to write everything out. Later, I'm going to simplify the steps a little bit, but okay. So actually, it's easier to move this term over here. Okay, so I'm going to group it like this. And I'm going to square whatever is inside the absolute value. I'll get u minus u naught squared. And you'll see why I'm doing this. Plus 2t v u minus u naught plus t squared, and then absolute value of v squared. Okay, now notice that we are deriving by t, and then we are evaluating the derivative at 0. Okay, so it's not always the case that the integral and the derivative can switch places, but for now, let's assume that we can do it, because in fact we can. And we're going to derive everything inside with respect to t. What does that mean? That means that anything without a t is going to become irrelevant. Furthermore, when we have a t squared, we're going to have a t left inside. So what's the derivative of t squared? It's 2t, right? And we're evaluating at 0. And therefore, this term disappears as well as this term. So we're left with 2t times gradient of u dot producted with gradient of v, and then we have 2t v u minus u naught. Okay, let me rewrite this. So now we have the integral of, and furthermore, 2 is non-zero, constant, so I'm just going to cancel it because I have 0 on the other side. So I have so the t just got derived, right? So these disappear as well. All right. And what I want to do now is I want to combine these two, right? So how do I do that? Well, I can use Green's theorem, right? Integration by parts. Because this part is then going to be equal to it's going to be equal to something evaluated on the boundary, and then I'm going to subtract the second derivative of u, or really the gradient of nabla u, and then I'm just going to multiply by v. But I didn't write anything here. I didn't write anything here because everything in here will be irrelevant. Why would it be irrelevant? Because v on the boundary is 0. Why? Because what does this mean? What does this space, oh, the highlighter isn't really showing. What does this mean? It means that we are evaluating, whenever we evaluate on the boundary, we end up with 0. So whatever I write here is just going to be 0, right? So what I wrote in yellow is going to be the second part of the integration by parts, which I shared in another video. And now I can just move this part down, and it'll be u minus u naught times v dx. Now notice v's, I can group the v's together like that. And this equation has to hold for all v, okay, for any function v. So what's the Euler-Lagrange equation? It is, and this negative is confusing, right? This negative belongs here, belongs inside. Okay, that looks better. So now our Euler-Lagrange equation, because v has to hold, because for all v, our integral is 0, anything here has to be 0, right? This is the Euler-Lagrange equation. So let's clear that up. It's going to be plus u minus u naught is equal to 0. This is it. All right.